So I will be presenting the paper called Moving Beyond Arbitrary Augmentations, K-hop Connectivity for Robust Augmentation in Graph Contrastive Learning. The paper mainly discusses the graph contrastive learning method, aiming node or graph classification for representation generation, and it proposes a technique for view generation through the contrastive learning. Now, the contrastive learning is a powerful self-supervised approach for node or graph classification when label data is scarce. In traditional supervised learning, a model learns by predicting labels and adjusting its predictions based on how close they are to the actual labels. But when labels are limited or unavailable, contrastive learning offers an alternative. Instead of learning from labels, it teaches the model by comparing or contrasting different views of the data. So here's how it works. If two views come from the same data sample, then the model learns to pull their representations closer together, meaning it increases their similarity. If the two views come from different samples, then the model learns to push them apart, minimizing their similarity. Through this process, the model captures useful patterns like in the data without relying on explicit labels. So that's the basic idea of contrastive learning. Next, we can look at how this framework is typically adapted for graph data. So the entire process can be broken down into three main stages. Firstly, the view generation. We have to first generate multiple augmented views of the input sample graph so that we can contrast between them and prepare our positive samples and negative samples to contrast. So graph augmentation can be stochastic, meaning randomly dropping nodes or edges. Then it can be adaptive, meaning dropping less important ones first, or augmentation less, meaning like deriving positive negative samples directly from the original graph. So suppose that I use GCN and GET architectures separately as encoders on the same original graph without any augmentation and treat their encoded representations as two distinct views. So that would be doing something without the augmentation. Now, next is network architecture. In the network architecture, we mainly develop our representations for both the views and prepare them for learning through the contrastive objective. Typically, the network architecture consists of encoder and projection head. Traditional GNN layers like GCN, GET, they are used as the encoder to get initial representations, HU and HV. Simple MLP layers are considered as the projection heads, which produce a more refined representation, ZU and ZV. Then lastly, the contrastive objective. A cost function is designed for the model to learn from, and the most generic cost function looks something like this in this formula in here, the total average mutual information formula. So let's dig deeper into it. Here, LUI-VI is a mutual information or agreement between the two representations, UI and VI, from two augmented views of the same node I that the model aims to maximize in the next epoch. So we want UI and VI's representations to be close when comparing because they originated from the same node. We also need to compare from the opposite direction, LVI UI, to ensure fairness. If we do not if we do that for all nodes and sum up these results and then divide it by 2 to average it, that should be our total average mutual agreement between the two representations from the two augmented views of the same node. Now, let's see how people generally measures the mutual information or agreement, LUIVI, for this formula. So LUIVI designed incorporating the positive and negative samples that we were talking about before. We can visually illustrate the process using node UI as the anchor. So a positive pair is formed between the anchor node in one view and its corresponding node in the other view. For example, U1 and V1. Since both represent the same original node under different augmentations, we want their embeddings to be close in the representation space. An intra-view negative pair is formed between the anchor node and all other nodes in the same view. For example, U1, U3, U1, U4, etc. That is represented in the second box here. Then lastly, the interview negative pair is formed between the anchor node and the non-matching nodes from the opposite view. For example, U1, V3 is one negative pair like that, and U1, V4 is another negative pair like that, and so on. So the formula is a function for negative log, so that the higher the value of this function is, the higher the overall mutual agreement score is going to be. And that function that fraction becomes larger when the numerator increases or the denominator decreases. That's exactly why we place the positive pair in the numerator and all the negative pairs in the denominator. So this matches our goal to maximize the similarity between the positive pairs and minimize the similarity with the negative ones. Also, you will notice we include everything in the denominator. That's mostly for scaling, ensuring that the score accounts for all the other possible comparisons. Now that we have walked through the general framework of graph contrastive method, it's easier to identify where some key challenges still remain. Most methods favor adding diversity at the cost of losing core structure when we are dropping edges randomly. It is possible that we may drop the core edges from the graph for one view, even though keeping it for the other view. Still, the encoder will fail to capture their similarity between them because one of the views do not have the core structure. So we propose to measure the importance of each edge and subsample it for view generation and then drop randomly from lower importance edges. Let's discuss it briefly. So for each node in the graph, we extract a subgraph that is included that includes all nodes within k-hops. The localized view helps preserve both close range and mid-range graph structures, and the extraction is based on counting the number of paths of exactly k-hops between the nodes. This process maintains patterns like clicks and ensures meaningful connectivity in the subgraphs. We assign an importance score to each node, to each edge based on how often it appears in these k-hop paths and whether it exists in the original graph. So the edges that are more central to the maintaining structure integrity, such as those forming cliques or connecting important sub-regions, receive higher scores. These high importance edges are kept during the augmentation. And instead of dropping edges randomly, we selectively remove the edges with lower importance scores. This controlled dropping reduces disruption to the graph structure, retaining the most critical connections while still introducing variation for robust training. We apply random masking to node features as well in a structured and consistent manner. Rather than masking the features completely at random, we use probability-weighted approach that ensures the important features are less likely to be removed. The same masking pattern is also applied across different augmented views to maintain fairness and consistency in the contrastive learning. So now let's walk through the overall framework that we have just proposed in simple words. We begin with the original graph. For each node, we extract k-hop subgraph as the basis of augmentation. These subgraphs are then passed through a view generator, followed by a GCN encoder. The encoded representations are projected and used in a contrastive loss function. The k-hop design ensures that semantic structures and neighborhood relations are retained, producing high-quality contrastive pairs. So our main contribution is in the view generation. While we are generating two views from the original graph, we are mainly converting into a k-hopped graph first and measuring the importance based on that graph. And from that k-hopped subsampling, we get our view 1 and view 2. That is our G1 and G2, which preserves the core structure of the graphs. So from a theoretical standpoint, our method improves contrastive view quality in two ways. First, by enforcing a consistent neighborhood structure through k-hop. Second, by limiting the view space to topologically meaningful subgraphs. We reduce noise introduced by arbitrary dropout or masking. This results in embeddings that generalize better, especially in low-level or noisy scenarios. Now, to evaluate our model, we conducted experiments on standard benchmarks like Quora, SciShare, PubMed, and Amazon Photo. So we compare against several strong baselines, including GRACE, GCA, and BGRL. We use linear evaluation on node classification tasks to assess representation quality. We also conduct ablation studies to isolate the impact of k-hop design and smoothing constraints. Here is a summary of our key results. Our method consistently outperforms the baselines on most datasets. We see significant gains in label efficiency, especially when label data is limited. The ablation study shows that the k-hop module alone provides a strong improvement, and the feature smoothing constraint further enhances the robustness. These results demonstrate the effectiveness and generalizability of our approach. To conclude, we propose a robust topology-preserving augmentation framework for graph contrastive learning. Our method is particularly effective in sparse or noisy settings and supports better generalization. As future direction, we plan to extend this approach to dynamic graphs and heterogeneous networks. We also aim to explore task-aware augmentation schemes and investigate deeper theoretical connections between graph topology and contrastive learning. Thank you.